Research paper is called Flow Models for Unbounded and Geometry-Aware Distributional Reinforcement Learning, and it's put out by a few institutions in Paris as well as IRT System X. Before we dive specifically into this research paper, I do want to make a note that I've gotten a ton of submissions for my internship that I made the video on, like a lot more than I was expecting overall. I will respond to people. Give me the weekend to go through. I've left these are my two inboxes, my main inboxes. If you're emailing me, you're emailing me to one of these inboxes, and you can see 21,133 and 973. Those are the unread in both these boxes. I don't check. I don't like it's part of that is cleanup, but as you can see, there's a lot of messages that I generally have to sift through. I get contacted a lot, but so I will reach out and contact every single person back that has emailed me with regards towards the internship. Thank you within that. And then so within that, let's dive into this particular research paper here. The interesting thing within this research paper is, to sum this all up, the big thing to me is that they essentially treat the distributional learning space, or the latent learning space with regards towards reinforcement learning as a fluid dynamic state is the best way to put that. And then so it's been kind of like a week or so since I put out any sort of I told you so video. And then so here we go. Here's another one of the things that I've been telling you for a few years now that I told you so. And then so in their abstract, we introduce a new architecture for distributional reinforcement learning that models return distributions using normalizing flows. This approach enables flexible, unbounded support for return distributions in contrast to categorical approaches that rely on fixed or bounded representations. It also offers richer modeling capacity to capture multimodality, skewness, and tail behavior than quantile-based approaches. It's more parameter efficient overall than categorical approaches, and it beats all of the standard metrics with regards towards distances, and then they make up their own distance metric within this, and they call it Kramer distance. It can be called lots of different things. They call it Kramer distance in this instance, but it's a geometry aware and computable directly from the return distributions PDF, avoiding the costly CDF computation. Bottom line within this, they take snapshots of the latent space as opposed to the actual data and the data set. Bottom line within this, like what this shapes up to philosophically, I'll start there because like that's the best place for me to start, right? Every single time that I see any sort of argument come out at this point where people are arguing against synthetic data, synthetic environments, etc., I just lol. Because that means that they have absolutely zero understanding of what exactly is going on within these models, because if they did, methods like this wouldn't work overall is the bottom line, right? And then what do I mean by that? What I mean by that is that any data set, any environment, given this context, what these models are doing, how they're working, and how these algorithms are working, and if this weren't true, none of this would work, is that essentially all of this, like the model's learning is all based off of representations anyway. Like if it's a data set, it's a representation of the data set. If it's an environment, it's a representation of the environment. What does that mean? That means that anything is a synthetic data set, or anything is a synthetic environment when it comes to these models. Even if it's a real world data set that you give it, the model doesn't learn on the real world data set, it learns on an abstraction of the data set. Like your data set would be the Platonic form. It's learning again, it's learning on a non-Platonic form, a non-perfect form, and a deviation of that data set that is a snapshot of it, an abstraction of it that it's taking and then warping in different ways in order to get about and essentially extract data from it is the bottom line within that. But so the bottom line within that is, I can't state it enough, every data set, every environment is synthetic. And then so the distinction when it comes to these models learning, at least when it comes to those, is a flat out misnomer, and it's a human construct overall. So traditional reinforcement learning algorithms aim to estimate the expected return from a given state or a state action pair. So they're going off of the Platonic state, right? However, this expectation provides only a partial view of the underlying return distribution, omitting critical information about uncertainty, risk, and variability. Distributional reinforcement learning addresses this limitation by modeling the full return distribution, providing a richer and more informative signal for decision making. It's taking that latent space and then saying, hey, there's more going on here within this latent space than like what your simple K means clustering algorithm is doing essentially. And then so within this, like there's a few papers and a few sites that they cite that like Bellamore et al. Showed that distributional Bellman operator is a contraction over a maximal form of Wasserstein distance. And then so like this is all, I mean, to me, this is all like they're building the framework for like if you take this to its logical conclusion that the latent space is a fluid dynamic based environment, right? That's essentially what they're saying within this, because everyone is usually the main equations are KL divergence, modeling these latent flows and latent spaces as manifolds, etc. As I've pointed out constantly on this channel now, that's not when you actually go through what these models are doing and you model them out, they don't model as manifolds. And so something needs to be fixed within that. Their solution to fix this, they call it Kramer distance. And then so here's the background. Essentially, it's a lot of mathematical equations, right? And then so bottom line is that what they do is they introduce this normalizing flow for distributional reinforcement learning. And then so like I've made like if you look at my Zyra videos and my Zyra model, this is a perfect example of like that, which is why I told you so, right? Because essentially what they're doing is they're measuring off of, again, the latent space of the model, right? But then they're recognizing that the latent space isn't a fixed latent space. It's not like there's fixed dimensions, that it's fluid, and that there's fluid dynamic rules within this latent space. And then so they compensate for that. And then by taking these metrics and then by taking essentially like all of these metrics and signals from these metrics, they're able to create a reinforcement learning algorithm that is better and trains better and learns better than ones that are designed like with your actual data set in mind. Like let's just train based off of the actual data set itself, right? And that's the difference here and what you're looking at here. And I mean, it's a ton of math that they go into, and then they utilize the Kramer distance as a loss function itself. And so that's the key part of it. Like that's what ties this into the geometry of this, right? So then they're proving like this Kramer distance, like I mean, like flat out, I'll call it what I think of it when I'm looking at this, which is a mixture of torque clustering, K furthest neighbors, and K nearest neighbors, is like and all concepts that I've gone over on this channel, and then half of those I've invented myself, and one of them I didn't. But that's what that algorithm flat out looks like overall to me, as to what it does in this instance. And then as you can see, here's their benchmarks and their performance. It scores very nicely within their results. And then so bottom line, this utilizing this Kramer distance as a loss function, what this does is this ties back to all of the geometry based claims that they make within this paper, right? And that I have made previously and a lot of times on this channel, which is that there's a geometric representation of the environment of your data set, etc. That is what the models are actually learning off of. And then you can actually take, if you don't believe that geometric representation exists, you can model it mathematically, you can play around with it, you can ping it, the models can recognize that it exists. So just because you can't see it, these models are detecting that it exists. That space is there. Like it's, to me at this point, it's like ultraviolet light, right? There exists whenever you create a mathematical space or a space in general, there exists space and features of that space that you can't see. Like, that makes sense to me. So that's all that this is essentially modeling out, right? And then so what does this look like in code? I like to take that to the next step. So here you go. Here's a Colab notebook for this particular NFDRL method, flow models for distributional reinforcement learning. And as an overview, this Colab notebook provides a Python-based skeleton implementation of the a normalizing flow distributional reinforcement learning model agent based off of their research paper. The goal of this framework is to model the full return distribution in reinforcement learning, offering a richer signal for decision making compared to traditional reinforcement learning algorithms that only estimate the expected return. The implementation focuses on using normalizing flows to create flexible, unbounded, and expressive return distributions. And that's kind of the bottom line, right? Get this full actual map of this, we'll call it fluid latent space that is going on and within these models. And the models are just picking up on that fluid latent space and giving you a map and an image based off of that. And then their map and their image correlates with the data set that you want to. And then so here's essentially how it all works, kind of like the breakdown of how it works, the functionality, dependencies, and then so again, this is a skeleton and conceptual implementation. It's intended for educational purposes, allowing users to understand the architecture and core mechanisms of the NFD-RL framework. It's not production ready or fully optimized implementation and would require further development, rigorous testing, and extensive hyperparameter tuning for application to complex reinforcement learning environments. This code aims to closely follow the descriptions and algorithms presented in the research paper overall. And so here it is. Here's the full structure. It's again all of their math, right? So I'm just taking it their Gaussian math that they put in here, like where they're making this kind of Gaussian mixture. Really cool overall to me, but that's a ton of the math here. And then you have the NFD-RL agent itself, which is again a ton of math. And then this is all part of the agent. Just this is and it's a lot of it's commented out, but I mean this is all literally part of the agent, and then the agent training. And then you have, in this instance, I'm training the model on an example usage. So this is all conceptual. So I have state dimensions, number of actions, number of mixture components, and number of flow samples for loss. So again, this is, again, I can't state it enough, right? It treats the latent space as a fluid dynamic environment. Who would have thought that? And then within this, they map it out, and then you train it from there like you would just with the typical training process. So we have number of episodes, max steps per episode, epsilon start and epsilon end. But then on top of that, we add an epsilon delay. So we have exploration fraction time steps and then total time steps. And then that's kind of some uniqueness, part of the unique fluid dynamics of how these environments work. And breaks down, and then we have our this is all again a conceptual training loop here, but I run it through, and then we can see that the loss goes down significantly over time. Like this loss is phenomenal by the end of this, although the reward, I generally don't want to see negative rewards, right? I would have been much happier if it had ended around here, or especially like here. And that loss rate would have still been phenomenal to me, as opposed to this loss rate, which is like magnitudes more less loss, but I don't like that negative reward at the end there. So just highlighting that out, I would be interested in testing this model overall to see why exactly it's getting that negative reward at the end, and highlighting that. But then so here you go. Here's the log of the actions, estimated Q values. So this is all Q learning based off of it's a modification of standard reinforcement learning. Again, it's just and it's Q learning, right? But it's just saying, hey, the Q, instead of the Q being real, it's the real is based off of an imaginary geometric concept that gets created based off of your data set, your environment, etc. And then let's just map the Q value to that. And then if it didn't exist, it wouldn't work. And then here we are with it existing and working. I'll leave a link to both the Colab notebook and this research paper. Again, I told you so. Flow models for unbounded and geometry-aware distributional reinforcement learning. Like this type of content, please like and subscribe. Thank you very much.